essentially to make these, what's nice about these tethered bilayer membranes, and now after years and years of reproducing the same experiment, we can say it's rather routine, is in order to make it, it's simply a two-step process where you mix the lipids and you get a self-assembled monolayer. So again, with a mixture of one of the tethered compounds and the beta-mercaptan-ethanol, and you lay it down on your surface. And then you basically add your lipids to fill in and do a rapid solvent exchange with an aqueous buffer. And that basically forces the self-assembly of the bilayer and, again, creates this buffer above and below the bilayer. So simply self-assembly of the tethers followed by assembly of the lipids through rapid solvent exchange. So making the lipid bilayers now is actually rather routine. And where we've been for the last couple of years is to really try to advance this platform as something that can be used to study membrane proteins. And this is again where we have the problem, the fundamental problem of oil and water. We have a lipid bilayer that is greasy and doesn't mind being close to organic-like solvents, or at least alcohols, and then we have proteins which are not happy in those similar alcohols, and so it's a question of how you assemble these proteins on the bilayers. So the first thing we were able to do, and there's a couple of examples of this that I'll show you, is you can add, if there's a membrane protein that's associated with the surface of your bilayer, these can be added after the bilayer has actually been formed. And so you can create the bilayer, exchange the buffer, and this, as I'll show you, has turned out to be a fairly robust and routine way to measure what happens to membrane proteins when they associate with surfaces,